Let me know if you're not able to see my PowerPoint slides or not able to hear me. Okay, just now we stopped at this tree table. Okay, just to run through, yeah, what are we covered just now? So this morning we introduce you. We introduce you this equation with this diagram with one-dimensional heat transfer in this direction, in x direction, and you're seeing the first conservation of energy, this equation, and then a small q sub x, and so on. So if you want to calculate for conduction, you use q sub x equal to negative k dt over dx. And if you want to calculate for convection, you use this one. Q sub h equal to h t minus t infinity. And if you only having a conduction, you use this equation. One-dimensional heat conduction equation, you use this equation. Kxx only, and there's no h inside, so this one only having a heat conduction. So you use this one. So if you're having a combination of two process, then you use this one with the HP divided by A. Again, P here is perimeter, not pressure, times T minus T infinity. So if you're having a combination of conduction and convection, you use this equation. Okay. So there's one small equation below on the screen here. If you have all the surfaces covered with the insulation layer and you allow one surfaces to for the heat transfer process, you will use this equation, minus k dt dx equal to h t minus t infinity. So later you will see this equation in a tutorial question later on, right? This tree table again, especially table 13-2 for material. Make sure you put it somewhere when you come to exam. Okay, for this session, we will look at one-dimensional finite element formulation with variation method. So again, we are using the 6 steps, like what you learned in chapter 6. So step 1, choose the element type. All right, step 1, choose the element type. As you can see on the screen here, you're having 2 type of scenario. The first one, you're having a element which is straight and it's very straightforward. You have a temperature 1 at 1 point and temperature 2 at point number 2 here. Well, what is the difference between the diagram A and diagram B? So as you can see, diagram B, you're having an equation for your T. So temperature 1, temperature 2, and there is a transition from temperature 1 to transition to point 2 through an equation. So in this case, you're having a T equal to NT1 plus N2 T2. So there is a difference between diagram A and diagram B. So you have to identify what kind of scenario you have. Either you're having a first scenario or second scenario. Okay, step 1, choose the element type. Step 2, choose a function for your temperature. All right, so there's a function for each element. So later we apply these 6 steps in the tutorial question. So for example, in this case, you're having a temperature function of N1 T1 plus N2 T2. So this is the temperature equation. By having a shape function, that what you learned in your chapter 3 and chapter 4, shape function, N1 equal to 1 minus x divided by L. N2 is x divided by L. All right, now the x here is the x location. For example, if your reference axis is at point 1, so your point 1, in point 1, the location of your x is 0. So if you apply this equation, your n1 value for point 1 will be 1. Okay, I repeat. So we are using n1 equal to 1 minus x divided by L, n2 equal to x divided by L. So what is the value if you look at point number 1? So point number 1, your x value is 0. Point number 2, your x value is L. So if you're looking at point 1, your n1 will be equal to 1 plus 0 divided by L. You get 1. Okay, so if you're looking at point number 2, your x is L. So if you look at point number 2, your n1 will become 1 minus L divided by L, where you get 0 for n1. And n2 will become 1, because at point 2, your x equal to L. However, for point 1, you don't have n2. For point 1, your n1 is 0, so both are 0. N2 is 0, n1 is 1. Okay, so this is how you calculate your n1 and n2. Yeah, so make sure this is the important equation for this second session. So because you need to calculate your temperature function. So you start with the general equation, T equal to N1 T1 plus N2 T2. And this is the standard equation for N1, or the shape function, N1 equal to 1 minus X divided by L, and 2 equal to X divided by L. It depends on the location you're looking at. So for example, if your reference axis at point 1, so point 1 location will be 0, 0. Point 2 location will be after you travel for the length L, the location or coordinate, Cartesian coordinate will be L, X, L, 0. So you just substitute the coordinate into N1 and N2, you will get the value. Then you substitute back into the temperature function. Okay, because later on in your Wednesday last lecture, you will apply into a two-dimensional scenario where you look at what you're doing in your ANSYS later on. Okay, so step 2 is a temperature function. And you should already know how to convert equation into a matrix form. So if you're looking at the screen here, if I write my function, my shape function into a matrix form, you should understand why I put a bracket, and inside the bracket, the first one is 1 minus X divided by L, because it's referred to this one. Second one is this one, yeah, and this one. So you should know how to put T function or temperature function into a matrix form. Okay. And this one is the displacement. In this chapter, we look at temperature. So T1, T2 is your displacement. Previously, in our chapter 3, chapter 4, when you learn about stiffness matrix, so this one we also learn about stiffness matrix. We just change the displacement into temperature. So this one, your temperature become T1, T2. Okay. In chapter 3, chapter 4, the displacement is U and V. So here you are having temperature. So if you want to put the temperature function in the simplified form or in matrix form, you write curly bracket T equal to bracket N curly bracket T. So it's taking the form of F equal to KD, that what you learned from the first chapter. So we are just changed according to the scenario. We are looking at heat transfer. So heat transfer relate with temperature. So T, capital T equal to N T. And every time you see capital, it means you're looking at the global scale, global dimension, right? Third steps, you find the temperature gradient divided by temperature or temperature gradient and the heat flux. So in chapter 3, chapter 4, you look at the stress and strain and the force over distance relationship. In this one, you change all the force into temperature, the stress and strain into heat flux and temperature. It's still the same concept, we just change according to thermodynamic process. Okay, in this case, we will use curly G as your temperature gradient. If you check chapter 3, is equivalent to strain matrix or analogous to strain matrix. So G equal to T divided by X. This is the temperature gradient. Or we can write in the bracket B times T. So this bracket B is what you learn in chapter 6, where you have the 9 equation to calculate the B. Okay, later I will show you. Slowly recap what you learned. So B equal to dN1 divided by dx and dN2 divided by dx. So this is the standard format. Okay, standard format. So when you come to final exam, you just look at my slides. You follow step 1 until step 6. Right? Just write all this equation out. You will get some marks there. Okay, recall what is your n, the shape function. So if you differentiate the first one with x, so if you differentiate 1 minus x divided by L, 1 becomes 0, minus x over L, you'll get 1 over L, negative. And you differentiate x divided by L, you'll get 1 over L. So this is how you get your B. The next one is for step 3, you need to find the heat flux over temperature gradient given by Qx. So again, you see Qx, it means conductivity scenario. So Qx equal to negative D matrix times the G. Okay, and G matrix is given above, bracket BT. So later you can substitute BT into this equation. So if you want to calculate the heat flux over gradient, so you have Qx equal to negative dBT equation. Okay, you just substitute here and there, you get the equation. And you are given for D is actually your Kxx. So chapter 3, step 3 is just to use the equation that you see on the screen here. Qx equal to minus dBT, because you substitute the temperature gradient. And substitute what is the D? D is Kxx, is the heat transfer that you have. It's a K matrix that you learned in chapter 3. Okay, in this case, it's a temperature, same concept. Step number 4, you look at the element dimension. You look for the element, what happened to the element. Okay, so given by this lengthy equation, all right, this lengthy equation. So if you're having a conduction, you use this equation, right? So again, just take note. If you have a conduction cases, you use this lengthy equation with the V integrate 3 times. You get why you have a integration of three integration here, because you integrate 3 dimension, you get volume. If you integrate 2 dimension, you get surface. All right, so how you identify the matrix or the equation, you look at the form of the equation, you know what you are finding. So for when you come to step 4, you look at the equation for conduction matrix, you find this equation. B already explained how you get B. B transpose times the D times the B dV. And this one, if you're seeing the H here, it means you're having a convection scenario. Every time you see H, means you have a convection. H N transpose and N ds. So this is an important equation. Yeah. So I did show you how to use the online matrix tools. So it shouldn't be a problem for you anymore. All right, as long as you know how to use it, and then you copy the answer from the website into your answer sheet. Okay. So again, you should know how to differentiate which one is for which one. So the first one is the normal conduction equation. If you're having a convection, then you add the second term inside your calculation. So the first one, conduction, second one, convection. Okay. So I extract from a textbook. For conduction part, if you want to find your K matrix, you use this equation. K sub C means for conduction scenario. K sub C equal to A KXX divided by L times the matrix form 1 minus 1 minus 1, 1. So this is a K matrix because later, this is for element, yeah, at the element dimension. Later, you need to superimpose into a bigger K in a global scale. So when you come to step 4, you look at element dimension, individual element. You use this K matrix to find it one. All right. So if you're able to write this equation out, you at least you score 1 marks for your exam. Yeah. So this is an important equation. K sub C A KXX divided by L times this one. Okay. So for conduction part, if you need to find the conduction process matrix for element, you find this one. You write this one and then look at the KXX given. All right. A is the area, L is the length of the element. Then you combine into a big global matrix later on. Okay, so for conduction, we already covered. For convection, you use this equation. There's a derivation there. I cut short already, so I just give you the importance equation to use. So if you write K sub H, it means convection, equal to HPL divided by 62112. Again, P here is perimeter, not pressure. So don't confuse with the symbol. H, every time you see H, it means convection. P is a perimeter. So this answer was answered by Katana just now. So Katana, don't make this mistake in exam. Yeah? HPL divided by 6. So you have three free marks here. So when it comes to step 4, you write this equation, you get 1 mark. You write this equation, you get 1 mark. You get this equation, you get 1 mark. So basically, I already give you 3 marks already. Yeah. Okay. So KC, KH, step 4. So when it comes to step, then you combine. So if you having a 2 scenario, you have a conduction and convection, you combine the matrix together. Okay. Kx equal to conduction plus convection. So another scenario is that when you have an open-ended convection. So if you're having an open-ended conducting medium and the ended is transferring some heat out, you need to add this equation at the back of the equation. So this term is for conduction. This one is for convection. And there is a leakage of heat at the end of the object there. You need to add this equation. So you add KH bracket sub n means that you're focusing on only of this process. Integration of H, this one, H transpose n times n ds. You add this equation inside there. Okay, so this page is important. Basically, it's summarized for step number 4. You write this equation, and you look at the scenario. If you need to consider the n conduction, or you are given a scenario where there's a curly arrow come out from the end, then you must add the third term inside the equation above. So mean that if you have conduction, convection, plus there's a leakage of the end, there's a 3 matrix in your step number 4. Means this one plus this one plus this one. Okay, if, yeah, so this is basically to summarize out the steps. So how do you calculate the last term here? So basically I give you all the calculation on the screen here, you can read through. So if you need to integrate the n here given by double integration, hn t n ds. So as you can see here, n1 equal to L. Yeah. So you're given the equation over here. N1 equal to 1 minus x divided by L, N2 equal to x divided by L. So at the end of location here, your shape function becomes 0. Okay, why 0? Because 1 minus L divided by L, because at the end here, the length is L. So you substitute x with the L. So 1 minus L divided by L is 0. And at the location here 2, your x equal to L, so you get 1. So your N1 equals 0, N2 0 for this location. Okay, this set of equation is for location number 2. Because you're looking at the convection process at point number 2. Then you substitute inside this equation, you'll get this one. So you write KHN, we are looking at the process at the end here, equal to the integration of your H, your N transpose, you write as 0, 1, times the N is 1, 0, 1, ds. So this is the matrix idea. So sorry for the, I should be using a bracket rather than the curly. Is a typo error over here. Just take note now. This is the, I should not use curly because curly bracket means something else. It should be bracket, yeah. Sorry for the typo error. Okay, then you continue with the integration. You will get HA bracket 0, 0, 0, 1. So this is the standard form for KHN that leak the heat flux out. Okay, so meaning when you come to step 4, you're looking at these 3 equations. First one, first set, if you have a conduction. Second set, you have a convection. And if you have a leak end here, you will be plus this equation, which is the next slide here, plus HA this bracket, meaning in this equation, you are plus HA 0, 0, 0, 1. This is a full set. If you're having a conduction, convection, plus the leak end here, your whole set equation will be this one, plus this one, plus this one. Okay. Of course, in the exam, you have to write all these steps, and then you write the end of equation of these 3. Okay. Don't straight away jump into this one. You have to write, you have to explain your steps. Okay. The next one, just now we only look at stiffness matrix. The next one we look at force. In this chapter, you need to find temperature and force. So the first one you find stiffness matrix, you combine them together. Second one you find for forces. Convection force is given by this equation. All right. So F convection N means at the end here, F convection N equal to H T infinity A times the shape function. So this one is for this case. Okay, so this is another one. If you need to find the force, and the force for thermodynamics or for heat transfer is in the unit of watt. Yeah? It's not in Newton, so don't confuse with the chapter 3, chapter 4. When it comes to chapter 7, you're looking at thermodynamics dimension. So be careful. force for convection in the unit of watt, W-A-T-T, watt. Then step 4, step 5, step 6, and even step 7 will be the same as the previous chapter. Step 4, you derive the matrix, you solve for the unknown, you combine, you get the global equation, you solve the missing parts. Okay. So let's look at one example, and then we will call it a day. Okay, look at the screen here. You're having a sample. There's a rod here, and you will be told that this pipe or this rod was insulated parameter, and you are having a h comma t infinity. Again, this is a hint for you. If you see h, it means you're having a convection process. And you're having a temperature on one side, 100 degrees C. On the left-hand side, the length is 480 meter, the length. And the radius is 1 meter for simplicity. Of course, in the exam, you won't see all these straightforward answer. Right, in this tutorial, you have a 1 meter radius subject, and the question asks us to do what? Let's look at the question. We need to determine the temperature distribution along the length, and then the temperature on the left is constant at 100 degrees C, and we have a free stream temperature which is 10 degrees C. So I already told you what is free stream, it is the T infinity. Let H is given, Kxx is given, value of H for forced air convection is given. All right, so this one is given, and in this tutorial, it will ask you to refer to table 13-2, 13-3. However, in exam, this line you won't see it. We assume you know how to find it already. So this tutorial is just to guide you through. Again, when it comes to exam, this line we will remove, and then we assume you know how to find table -2, table -3. Okay. All right. Let's try to solve this question. So normally we will break the object. We call it discretization or the meshing process when you use ANSYS. So the first step here, we also do meshing. So what we do, we break the object into 4 pieces. So as you can see from the question just now, the total length is 480 meter. We break into 4 pieces. We break into 4 pieces, where each pieces is 120 meter, 120, 120, 120. So we're having 1, 2, 3, 4. We circle it with a number, means that we have an element 1, element 2, element 3, element 4. And we have a node 1, node 2, node 3, node 4, node 5. So this one actually is the same principle as what you learned in your chapter 3 and chapter 4 for your stiffness matrix. Okay, so it's the same. Only this chapter you change all the force into temperature. Okay. All right. So any question on these steps before we move forward? Any question for breaking into 4?
Okay, so this is 480, so it's easier with the 120, right?
Yes.
I don't know if we can get, is it possible to, is it like if you have more elements, okay, of course it's more calculations, but does it like increase the accuracy of the answer?
Yes, because why we break into 4 or even into a smaller pieces, because it will help us to it will cut short the equation, especially if you have a big number over here. If you want to calculate 480 meter, it will be a very lengthy equation later on. If you break into small one, you only need to look at repeated element later on. You will see in the following steps. So the first step is we break the whole object into individual pieces, like what we did in the ANSYS program, we do meshing. So the first step we break into 4. Okay, later you will see why we're doing this one. Yeah. Okay. So only we need to take note is that there is a convection happen at the end here. Here, there's a convection process. There's a heat transfer at this end. So we need to take note on this section when we calculate later on. Yeah. So I pull out the first equation that I keep mentioning just now. We look at the K matrix, right, or the conductivity matrix. As you can see here, I'm using a small k. It means that we look at element first. So if I write capital K, means we already look at the global dimension, where we already come to the last few steps already. So for chapter 7, normally you will start with this red color equation. K, small k equal to kxxl and so on. So again, the first term here is conductivity. Second one is the convection. I'll put it H. The third one, we add this one because we have an open end here. That's why we add this term here. Okay. And why we do not put the equation HA and bracket 0, 0, 0, 1, because the end shape here will be changing according to cases. So you need to be careful. It's not usually this one, but you need to be careful, right? You need to know what is n just now. So you can look back at the slides. Huh? Okay. So we calculate for each of the element. So I do it one set for you. So you can see the element 1, element 2, element 3, element 4 actually is symmetrical. So we just substitute the area. How we calculate area for a rod is we take pi r square, right? So pi r square. So you have pi, your r is 1 meter, so 1 meter square. Kxs is given in the question. So Kxs is 20 watt over meter Celsius divided by length. We are looking at element here. So element is 120 meter. So you already calculate. So basically for chapter 7, first step, you write the equation, which is the one in red color. Then you calculate for individual element, the stiffness matrix. You calculate all this constant value. You calculate K, AK divided by L. You calculate HPL divided by 6. What is that? Right? You calculate all this value, you substitute inside this equation, and then you follow with the remaining steps. So the first step, you calculate AK divided by L. You get this one. So you get 0.5 lah. Right, so for this module, maximum decimal place 3 decimal place, minimum 2 decimal place. Huh? Okay, so in this case, I give you 4 decimal place. It's more than enough. Yeah. Unit is watt over meter Celsius. For this module, unit is important. Huh? Right. So just give you some idea. If this one costs you 2 marks, you forget to put in value, you only get 1 mark. If this one is 2 marks, you forget to put in the unit, you only get half of the marks. Yeah? Discount 50% if you do not write unit. So you get AK divided by L. You get one value. The next one, you just substitute the value inside there. For element 1, if you look at this element, you don't have convection happen. You cancel the second term and third term. Yeah. So for element 1, we is only look at this one. We don't have an open-ended here. We don't have a convection. So you cancel. You put arrow there. You put 0, and then you write there's no convection for element 1. Same, you repeat the same process for element 2, element 3. You need to calculate now. You need to calculate the value. Same. So in this case, your K element matrix for 1 it will equal to 2 equal to 3. So you can write in this form. and then you repeat you repeat this answer in your answer sheet, right? So you repeat this one, you just change the note here, the super note here. Change to 2 equal to this one, K3 equal to this one. Okay, any question for element K matrix? Why suddenly we cancel this one, you understand? Because it's connected. The element 1, 2, 3 is connected and there's no open-ended convection happen. So that's why we can cancel the second term and third term here. Okay, quite straightforward for chapter 7. You look at the dimension, you look at the scenario, you break into small pieces, then you judge based on the scenario you have. If it's not open, you cancel. All right. So for element 4, we have a special treatment for that. So because it's have an open-ended, then you can only cancel the middle one. Okay, because in this case, we don't, for element 4, we don't have the middle one. We don't have a convection happen inside here, but we have an open-ended section at the end here. Okay, so for element 4, you can only cancel the second term here because we don't have convection happen inside the rod. Okay, so there's a side note there. That's why we cancel the second one. So for element 4, you have two metrics. One is for conduction, and then one is the convection at the end. All right. Now in this case, it's a straightforward like the example that we have. So we can straight away write the convection at the end, HA bracket 0001, and then you have all the element metrics already. Okay, so to solve this kind of question, the first step, you write the general equation. We did this one. Then you calculate the stiffness matrix in front of here, this one, all this. Then you look at element 1, what is it? Does it expose to, does it open? If not open, you can cancel. And you look at it, if it's connected, then you don't have convection happen. You can cancel. So you only left out one term there. So it will be the same for element 1, element 2, and element 3. But element 4, you need to be careful because element 4 is open-ended. However, element 4 was connected to element 3, so there is no convection happen. Sometimes the question will help you. You will mention, do not consider convection inside the element. So you can cancel this one. All right. So you get the 4 fundamental equation. Okay, the rest is just calculation. So for element 4, the first term, AK divided by L, you already calculated 0.5. And you just substitute H is given in the question, 10. Area of the rod is pi r square, again, pi r square. And you calculate based on the matrix here. All right, so you have the K matrix element for element dimension. We do the addition between two matrices. So you'll get this matrix. The next one, you just superimpose. Okay, so this one is a add-on equation. If you need to find the forces, there are 4 equations on the screen here. They are quite standard. So if you have a heat transfer, capital Q happen, then you use the first equation where you write bracket, curly bracket F means you're finding force, curly bracket F, Q equal to this one, QAL divided by 2 bracket 1, 1. All right. If you have a heat flux happen inside the element, you use a second equation, F sub Q equal to Q star PL divided by 2, 1, 1. if you have a convection process, which normally you will have, you write curly f sub h equal to ht infinity PL divided by 211, and you're having a open-ended leakage of heat energy, then you use f sub h curly, write the n there to differentiate this equation with this equation. All right. If you have open-ended, you need to write a sub n in your equation. So try to differentiate between this one and this one. Is that different? Not different. Not same. It's different. So, and then you write this equation. So this page is important to help you to score some marks in final exam also. So these 4 equations, you can choose based on their scenario. If you are given the Q is happening, the capital Q is happening, then you calculate this one. If you are being told that there is a Q star, then you use this one. If you're having a convection force, then you use this one. And your object is exposed, you add one more forces in the equation. Okay, so basically this is you look at the scenario and then you use accordingly. So if you combine these 3, you get this one. So QAL plus Q star PL plus H TPL divided by 211. So let's say when you need to use this equation is when you have a Q scenario, you have the Q star scenario, and you have a convection scenario, then you use this equation. So in the later chapter, we will see how we use this equation. So for this first tutorial question, because we don't have heat source, so your capital Q 0, you don't have heat flux happen in the system, so Q star equals 0. And there is no convection happen except the n. So these 3 you can cancel out. This equation cancel, so this equation doesn't apply for this scenario. You only need to consider this equation for this example. Okay, so it's quite straightforward. You look at a question statement, whether the question say that is there any heat source? If no heat source, you don't need to consider the first equation. If no heat flux, you don't need to consider second equation. If no convection, you also don't need to consider the third equation. Usually they will be open-ended at the end. So normally by force you have to use the fourth equation. So this, at least you should write this equation in your answer. So this one you will score 1 mark if you write this equation. Okay, so we move forward. There are some side note there. So if you are having a heat source, you will get positive force. You get a heat sink, you get a negative force. If you have a flux positive, means you go into the surface, and so on. So this is just a side note for you. It's just to help you to explain. When you get your force negative, what does it mean? When you get your force positive, what does it mean? Okay, it's also part of the final exam question. So on. So let's back to our question. So I already explained why we can cancel these four equations on the screen here, and we'll only focus on the one on the right here. So force as element 1, 2, 3, 4 is 0 because we don't have all the heat source, we don't have heat flux, and we don't have convection happen for element 1, 2, 3. But element 4, yes, we have one force at the end here. So we write force for element 4. Okay, follow the notation that I use for this module. So curly F superscript 4 equal to HT infinity A matrix 0, 1 to calculate the forces for this element. And again, force for chapter 7 is in the unit of watt, not in the unit of Newton. Okay. So you substitute the value given. H is given is 10. Temperature is given 10 degrees C. Area, you calculate the cross-section area of the rod. Rod is area is a circle, so pi r square. And the metric is 0, 1. You do the multiplication of this mathematic model. You'll get 314 point something watt. So why you have two terms here? It means that because you look at element 4 you have 0.4 and 5. So this basically refer to 0.4, not 4. This refer to 0.5. Okay. So this one refer to this one. This one refer to this one. Okay, like matrix lah, like what you learned in your chapter 3 for displacement. Okay, the next one, we just look at the element stiffness matrix. We combine, become the capital F and K. So F equal to KD, but in this case, we look at thermodynamics problems. So F equal to KT temperature. You find the superimpose all the element matrix into global matrix. So I'll show you the steps. So element 1, you get this matrix. Element 2, same with 1. Element 3, same with 1. Element 4, you have this one. You superimpose all these matrix again. All these numbers in front, it give you different location. Element 1, you look at 0.1 and 2. Element 1, you have 0.1 and 2, so 1 and 2. However, for element 2, you're having 0.2 and 3. Element 3, you have 0.3 and 4. And for element 4, you have 0.4 and 5. So be careful when you park your number. You'll be like your parking lot in a multi-story building. So be careful on the matrix superimpose steps. It will arrive at this one. So I will just straight away give you the answer. You should understand. So I help you a little bit on force. F1 equal to Fy column. F1 equal to something. All right. Then you superimpose all the K matrix here. And T1, T2, T3, T4, the blank space is 0, yeah? The blank space is 0. Okay. Then you continue, you should get this one. So this one you take as your homework. Try to look at this example and then try to understand what is happening. All right. So basically it's a F equal to Kx. But in this case, we are looking at temperature. So F equal to Kt temperature. Superimpose the K matrix you already learned since your chapter 2. So you should be very skillful in this portion. Force, you look at the force that you find. So in this case, for point number 5, you already have force 314.159. So just now you calculate for the force just now for element 4, this one. Because you have an open-ended, you use the equation of this equation to find 314 watt just now. So you put inside the matrix and then you solve. You have 5 equations here. You try to solve. So I'm going to introduce you one new method or strategy using it. So pay attention. A little bit different from the previous chapter. So we are making full use of the boundary condition in the following steps. So the temperature of 0.1 is given. So temperature T1 in the matrix, you know. So we try to modify the matrix equation here. So since we know the temperature of T1, we make full use of the equation that we know. So we know T1 equal to 100 degrees C. We modify the matrix accordingly. So these are the other steps lah. So if you have if you look at node 1, how you find node 1? Node 1 is 0, right? 0 equal to negative T1. So these are the equation you calculate from the node process. Okay. So you take these steps. So 0 equal to this one times this set. So this one minus 0. How you get this equation? You take negative 0. So this is 0, 0. How you get this one? Is negative 0.5236 times T1. You get this one. Then plus 1.04 times T2 plus negative 0.5 times T3 and 0, 0 behind we don't have. So you rearrange, you'll get 52.36 equal to 1.04 something T2 minus 0.5 T3. Any question for these steps? No, huh? Okay, I'm forward, huh? So we choose the second line to calculate, and then we transform. We try to compare what is happening from the top matrix into the bottom matrix. We change the matrix above to matrix below. This one become 100 degrees C. So you can see that the row and column, the first row and first column become 1, 0, 0, 0, 0, 0, 0, 0, 0, and this one become T1. So you get 100 degrees C for T1. So if you get this one times this one and this one, you get this boundary condition. And this one, I already show you how to get 52.63 and you modify accordingly. How you get 1.042 negative 0.5 here through this equation. Okay, we modify the first two equations based on boundary condition. Treat this as your homework. Yeah, go and carefully study how you transfer from the top equation to the below equation by using a known boundary condition. In this case, normally will be given T equal to something Celsius. You need to know how to change according to this concept. Okay, once we have it, then you are having 5 simultaneous equation here. All the value you know for the left hand side, K matrix, all is given, only missing 5 unknowns. So 5 equation, 5 unknown, you're able to solve. You are allowed to use the online matrix calculator to find. I already show you how to use it. So you just inverse this matrix times this matrix, you're able to get T1, T2, T3, T4, and T5. Very straightforward. But you have to copy back the answer back into your answer sheet. Right? Be careful when you key in all the numbers. So when you key in into the online matrix, I recommend you to use 4 decimal place for accuracy. Okay, but is enough to use 3 decimal place, right? Okay, so we have done for the first tutorial question. We'll look at it a few more example on this Wednesday. Okay, so let me stop the recording.